Every time you send an email or buy something online or even just check your bank account, you're being protected by this invisible shield of encryption. But there's a new kind of computer coming, and it's one that threatens to just completely shatter that shield. So today, we're going to break down this quantum threat and figure out what it really means for our digital world. This statement from Isaka really hits the nail on the head, doesn't it? This isn't science fiction anymore. It's just a question of timing. The race is on, right now, to get our defenses ready before all of our digital locks become completely useless. Okay, so before we get to the scary stuff, let's first get a handle on the shield that we all rely on every single day. We're going to do a quick rundown of how modern cryptography actually works to keep all of our information safe. At its heart, encryption is actually pretty simple. You start with what's called plain text, message you can actually read. Then the encryption process, using a secret key, scrambles it all up into ciphertext, which to anybody else just looks like total gibberish. Only the person with the right key can unscramble it and get that original message back.
So, this all basically boils down to two main flavors of encryption. On one side, you've got symmetric key. Think of it like a shared house key. The same key locks and unlocks the door. It's super fast, but its big weakness is, well, how do you get that shared key to the other person securely, especially over the open internet? And that's where public key cryptography comes in. It's a really clever trick that uses two keys. Anyone can use your public key, the one you share with the world, to send you a locked message, but only you have the private key to actually open it. It's what lets us talk securely to anyone, anywhere.
And we're not talking about just a few things here. This shield protects, well, pretty much everything. From your online shopping and all your passwords, all the way up to military communications and top state secrets. Our entire digital economy, our national security, it's all built on this foundation.
All right, so that's our shield. Now let's talk about the thing that's threatening to break it. A quantum computer isn't just a faster laptop, not even close. It's a completely different way of computing that can solve certain problems that our normal, classical computers, well, they can't even touch. And this is the million-dollar question, right? If our codes are so strong today, what is it that makes a quantum computer so different? Let's get into it. The thing is, our encryption isn't some magical, unbreakable force field. It's what we call computationally secure. All that means is that the math problems it's based on would take a normal computer millions, maybe even billions of years to solve. We've literally built our security on the idea that some math is just too hard to be practical. To get a little more specific, the algorithms you see everywhere, like RSA and ECDSA, they're built on two of these hard problems. One is factoring gigantic numbers into their prime building blocks. The other is something called the discrete logarithm problem. For a classical computer, these are just impossible tasks. But, and this is a huge but, here's the catch. Back in 1994, a mathematician named Peter Shor came up with an algorithm. And this algorithm, if you run it on a quantum computer that's powerful enough, can solve those exact problems with terrifying speed. It's like someone discovered a master key that just happens to fit the very specific, very popular locks we use to protect, well, everything. Now, you might be thinking, okay, but these super powerful quantum computers don't exist yet, so what's the big deal? And that right there is why this is such an urgent problem. It's all because of a strategy called harvest now, decrypt later. It's a simple, incredibly patient, and honestly, a terrifyingly effective strategy. Step 1. Adversaries, right now, are capturing and storing enormous amounts of our encrypted data. Step 2, they just wait. And step 3, the moment a powerful quantum computer is ready, they can go back and decrypt every single thing they've collected over the years. Just think about how long some data needs to stay secret. Government secrets, corporate intellectual property, your own private health records. This stuff has a lifespan of decades. Waiting 20 years is nothing for an adversary who can suddenly unlock the secrets of an entire generation all at once. The data being stolen today is absolutely vulnerable tomorrow. Okay, so that's the bad news, a lot of it. But here's the good news. The world's top cryptographers are already on the case. We are right in the middle of one of the biggest security upgrades in the history of the internet, forging a whole new kind of digital armor. And this isn't some secret backroom effort. The U.S. National Institute of Standards and Technology, you'll hear them called NIST, has been running a global competition for years to find and standardize the next generation of cryptographic algorithms. The goal is to find ones that can stand up to attacks from both classical and quantum computers. So here you can see the upgrade in action. We're literally swapping out the old, vulnerable math problems, like factoring, with totally new families of problems. These new methods, things like lattice-based and hash-based cryptography, they're built on math that we believe is hard for all computers to solve, quantum ones included. We're diversifying our defenses.
And that right there is the key. That's the whole idea. We're not just making the old math problems a little bit bigger, we're switching to fundamentally different and much, much harder problems. This is the core of what we call post-quantum cryptography, or PQC. So we have these new algorithms, which is great, but how in the world do we actually get them running across the entire internet on all our devices? I mean, that is a monumental engineering challenge, and the answer lies in adopting a new strategic mindset. The really important concept here is something called crypto agility. It just means designing our systems so that we can swap out cryptographic algorithms easily. It's like being able to change the locks on your house without having to rebuild all the doors. If we build for agility now, then the next time a threat comes along, we won't have to start this whole massive global upgrade from scratch. Of course, this is way easier said than done. It's not like you can just flip a switch. These new PQC algorithms, they often have larger keys, they need more processing power, and that can be a real problem for smaller devices. And trying to integrate them into systems that are decades old, that's a huge challenge. And frankly, there's a shortage of people who have the expertise to do it right. So, what should organizations be doing right now? It's pretty straightforward, really. You can't protect what you don't know you have. So step one for any company or government agency has to be creating an inventory of all their crypto. Only then can you actually assess your risk, plan a migration, and start testing out these new standards.
Look, the main takeaway from all the security experts is pretty clear. This isn't about panicking. It's about careful, methodical preparation. This transition is going to take years, and for it to work, the planning needs to start today.
So let's put this on a timeline, just to get a feel for how this is all going to play out. Right now, in 2025, the standards are getting finalized, and this is when organizations really need to be doing that inventory and planning. Over the next 5 to 10 years, you're going to see a lot of hybrid systems, ones that use both the old and new crypto at the same time for a safer transition. The really widespread migration to fully post-quantum systems, that's going to happen as we get closer to the 2030s and beyond, right as the quantum threat itself starts to feel a lot more real.
It really puts the scale of this whole thing into perspective, doesn't it? Our entire digital world was built on one very specific type of math, and now we have to rebuild it on another. This is one of the most significant, most complex security migrations ever attempted, and honestly, its success is going to determine the future of our secure digital world. The question really isn't if we're ready. We have to be.